What would happen if we decided to leave the solar system? Imagine drifting beyond everything humanity has ever known, past the familiar planets and moons, past the icy remnants at the edge of our cosmic neighborhood, and into the vast emptiness between the stars. This journey is one of the most profound thought experiments we can undertake, because it forces us to confront the true scale of the universe and our place within it. Tonight, we will explore what actually happens when we leave the solar system, examining the strange and wondrous phenomena that await beyond the boundaries of our sun's influence. The solar system does not end with a clear boundary like a fence or a wall. Instead, it gradually fades into interstellar space through a series of transitional regions that scientists have only recently begun to understand. The outermost planets give way to belts of icy debris, which in turn yield to the farthest reaches of the sun's gravitational and electromagnetic influence. Beyond all of this lies the interstellar medium, a realm so different from anything we experience near Earth that it almost defies comprehension. Let us begin with something remarkable that few people know about. The boundary of our solar system is not spherical, as most illustrations suggest. It is actually shaped more like a comet, with a long tail stretching behind the sun as it moves through the galaxy. This shape is created by the pressure of interstellar gas and dust pushing against the bubble of solar wind that our sun creates. The sun is not stationary. It is hurtling through the Milky Way galaxy at approximately 490,000 miles per hour. And this motion creates a bow-shaped front and an elongated tail in the heliosphere, which is the technical name for the sun's sphere of influence. The heliosphere itself is a fascinating structure that extends far beyond the orbit of Pluto. It is essentially a giant bubble of charged particles streaming outward from the sun, creating a protective cocoon around our entire planetary system. This bubble shields us from much of the harmful cosmic radiation that fills interstellar space. When we talk about leaving the solar system, we are really talking about leaving this protective bubble and venturing into an environment that is fundamentally different from anything we have experienced. One of the most surprising discoveries in recent space exploration came from the Voyager spacecraft, which have now traveled farther from Earth than any other human-made objects. When Voyager 1 crossed into interstellar space in 2012, scientists discovered something unexpected. The boundary region is not a smooth transition, but rather a complex zone filled with what they call magnetic bubbles. These bubbles are created by the interaction between the sun's magnetic field and the interstellar magnetic field, and they form a frothy, turbulent region that the spacecraft had to pass through. The temperature at the edge of the solar system is also counterintuitive. While you might expect things to get progressively colder as you move away from the sun, the reality is more complex. In the region where the solar wind slows down and begins to interact with interstellar space, called the heliosheath, temperatures actually increase dramatically. This happens because the solar wind particles are compressed and heated as they collide with the interstellar medium. Temperatures in this region can reach hundreds of thousands of degrees, though because the particles are so sparse, a spacecraft passing through would not actually feel hot in the conventional sense. Beyond the heliosphere lies the interstellar medium, which is the material that fills the space between the stars. This is not simply empty vacuum as many people imagine. Instead, it is an incredibly diffuse mixture of gas and dust, primarily hydrogen and helium, with traces of heavier elements. The density of this material is astonishingly low, typically only about 1 atom per cubic centimeter. To put this in perspective, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimeter. The interstellar medium is essentially the closest thing to a perfect vacuum that exists naturally. Yet it is not truly empty. The dust particles that drift through interstellar space are themselves quite interesting. They are typically only a few micrometers in size, smaller than the width of a human hair, and they are composed of silicates, carbon compounds, and water ice. These tiny grains play an important role in the chemistry of space, providing surfaces where atoms can come together to form molecules. Many of the complex organic molecules that have been detected in space are thought to form on the surfaces of these dust grains. If a spacecraft were to leave the solar system and travel through interstellar space, it would immediately notice a change in the radiation environment. Inside the heliosphere, we are partially shielded from galactic cosmic rays, which are high-energy particles that originate from supernovae and other violent events throughout the galaxy. Once outside the protective bubble of the Sun, a spacecraft would be exposed to significantly higher levels of this radiation. For human explorers, this would pose serious health risks, as galactic cosmic rays can damage DNA and increase the risk of cancer and other diseases. The magnetic field in interstellar space is also different from what we experience within the solar system. Rather than being dominated by the Sun's magnetic field, which spirals outward like water from a rotating sprinkler, interstellar space has its own magnetic field that is shaped by the galaxy as a whole. This field is relatively weak, only a few microgauss compared to Earth's field of about half a gauss, but it extends across enormous distances and plays a crucial role in shaping the structure of the interstellar medium. One of the most profound changes that would occur as we leave the solar system is the appearance of the stars. Inside our planetary system, the Sun dominates the sky so completely that we can only see other stars when we are in shadow or during nighttime on Earth. But once we traveled beyond the heliosphere, the Sun would begin to appear as just another star, bright but no longer overwhelming. At the distance of the Voyager spacecraft, the Sun appears roughly as bright as Venus does from Earth on a clear night. Travel farther, and it would continue to fade until it became indistinguishable from the countless other points of light in the sky. This brings us to one of the most psychologically challenging aspects of interstellar travel. The distances involved are so vast that our normal sense of space and time breaks down completely. The nearest star system to our Sun is Alpha Centauri, which is approximately 4.24 light-years away. This means that light itself, traveling at 186,000 miles per second, takes more than 4 years to make the journey. At the speed of the Voyager spacecraft, which are moving at about 38,000 miles per hour, it would take approximately 70,000 years to reach this nearest stellar neighbor. The space between stars is not uniformly empty. Instead, it is filled with structures that astronomers have given evocative names, like stellar nurseries, supernova remnants, and the local bubble. Our solar system is actually located within a region called the local interstellar cloud, which is a relatively dense patch of gas about 30 light-years across. This cloud is itself embedded within a much larger structure called the local bubble, which is a region of extremely low-density gas created by ancient supernovae that exploded millions of years ago. The local bubble is roughly 300 light-years in diameter, and our solar system has been traveling through it for at least the past 5 million years. The walls of this bubble are denser regions where the material ejected by those ancient supernovae has accumulated. If we were to leave the solar system and travel far enough, we would eventually encounter these denser regions, where the interstellar medium would become noticeably thicker. The composition of interstellar space varies significantly depending on location. Some regions are dominated by neutral hydrogen, where atoms drift peacefully without electrical charge. Other regions contain ionized gas, where atoms have been stripped of their electrons by intense radiation from nearby stars. There are also molecular clouds, which are dense enough that atoms can bond together to form molecules like water, carbon monoxide, and even complex organic compounds like amino acids, Scientists have detected more than 200 different molecular species in interstellar space, including some that are quite surprising. Ethyl alcohol, the same compound found in alcoholic beverages, has been detected in vast clouds near the center of our galaxy. Amino acids, the building blocks of proteins, have been found in meteorites that formed from interstellar material. These discoveries suggest that the chemistry of life may begin in the cold depths of space, long before stars and planets even form. The question of whether we could actually survive a journey through interstellar space is one that scientists take seriously. Beyond the radiation concerns already mentioned, there are numerous other challenges. The spacecraft would need to carry enough fuel and supplies for a journey lasting generations, or even millennia. It would need to maintain its structural integrity against the constant bombardment of interstellar dust particles, which at high velocities could punch through metal like tiny bullets. And it would need to navigate through space without the familiar reference points of our solar system. Some researchers have proposed novel solutions to these problems. Solar sails, which use the pressure of light to accelerate spacecraft, could potentially reach much higher velocities than conventional rockets. Laser propulsion systems could boost tiny spacecraft to significant fractions of the speed of light. And nuclear pulse propulsion, which involves detonating small nuclear devices behind a spacecraft, could theoretically achieve speeds that would make interstellar travel feasible within a human lifetime. The concept of generation ships has also been explored, where entire self-sustaining communities would live and die aboard spacecraft during journeys lasting centuries. These vessels would need to be essentially complete ecosystems, capable of recycling all resources and maintaining stable populations over many generations. The psychological and social challenges of such a journey are difficult to imagine, as the travelers would be born, live, and die in the vast emptiness between the stars. Let us turn now to what the voyage itself would be like. If you were aboard a spacecraft leaving the solar system, the early stages of the journey would be dominated by the familiar sights of our planetary neighborhood. The gas giants Jupiter and Saturn would pass by, their magnificent ring systems and swirling storms visible through your windows. The ice giants Uranus and Neptune would appear as pale blue dots against the blackness of space. Beyond Neptune lies the Kuiper Belt, a ring of icy debris left over from the formation of the solar system. This region contains millions of objects ranging from small comets to dwarf planets like Pluto and Eris. The Kuiper Belt extends from roughly 30 to 50 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. Passing through this region, you would see countless chunks of ice and rock drifting in the eternal cold, preserved almost unchanged since the solar system formed 4.5 billion years ago. Beyond the Kuiper Belt is an even more distant region called the scattered disk, where objects have highly elliptical orbits that can take them hundreds of astronomical units from the Sun. These objects were likely disturbed by gravitational interactions with Neptune and flung into these extreme orbits. The scattered disk merges gradually into the Oort Cloud, which is perhaps the most mysterious region of our solar system. The Oort Cloud is a theoretical spherical shell of icy objects surrounding the Sun at distances ranging from 2,000 to 100,000 astronomical units. We have never directly observed the Oort Cloud because its objects are too small and too far away to detect, but astronomers believe it must exist based on the orbits of long-period comets. These comets, which take thousands or millions of years to complete a single orbit around the Sun, must originate from a distant reservoir of icy bodies. The outer edge of the Oort Cloud represents the true gravitational boundary of the solar system, the point where the Sun's gravity becomes weaker than the gravitational pull of nearby stars. Objects in this region are only loosely bound to our Sun, and can be easily dislodged by passing stars or by the gravitational tide of the galaxy itself. Every million years or so, a star passes close enough to the Oort Cloud to send a shower of comets tumbling toward the inner solar system. Traveling through the Oort Cloud would be an eerily quiet experience. The objects in this region are so spread out that you could travel for thousands of years without seeing a single one. The sun would have faded to just another bright star, and the familiar constellations of Earth's sky would begin to distort as your perspective on the stars shifted. Stars that appeared close together from Earth would separate, while stars that seemed far apart would draw closer. Beyond the Oort Cloud, you would officially leave the solar system and enter true interstellar space. This transition would not be marked by any dramatic change. The blackness of space would look the same. The stars would shine with the same steady light. But you would have crossed an invisible boundary, leaving behind the gravitational embrace of the sun and becoming, in a sense, a citizen of the galaxy rather than a child of our particular star. The journey from the outer Oort Cloud to the nearest star would take an unimaginably long time with current technology. Even traveling at 1% of the speed of light, which is far faster than any spacecraft we have built, the trip to Alpha Centauri would take over 400 years. At more realistic speeds, the journey would span millennia. The space you would cross during this time is not completely empty, but it is emptier than any laboratory vacuum ever created on Earth. The interstellar medium has a kind of weather, with variations in density and temperature that shift over millions of years. There are interstellar winds, caused by differences in pressure between regions of space. There are magnetic storms, triggered by the passage of shock waves from distant supernovae. And there are cosmic ray storms, when particularly energetic particles from violent events wash through the galaxy. Your spacecraft would also encounter something called the galactic tide, which is the differential gravitational pull of the galaxy on objects at different distances from the galactic center. This tidal force is extremely weak, but over the vast distances of interstellar travel, it could gradually alter your trajectory. Navigation between the stars would require constant adjustments to account for these subtle forces. The stars themselves are not stationary targets. They are all moving through the galaxy on their own orbits, some faster and some slower, some toward us and some away. The star that is closest to us today may not be the closest in a million years. Planning an interstellar voyage would require predicting where your destination star will be when you arrive, not where it is when you leave. As you approached another star system, you would begin to notice changes. The interstellar medium would thin out as you entered the stellar wind of your destination star. You might pass through a region similar to our heliosphere, where the star's influence creates a bubble in the interstellar gas. And eventually, you would see the star grow from a point of light to a disk, and any planets orbiting it would begin to reveal themselves. What kind of star system might you find? Our galaxy contains an enormous diversity of stellar configurations. Some stars are solitary like our Sun, while others exist in binary or even multiple star systems, where several stars orbit around each other. Some stars are much larger and hotter than our Sun, burning through their fuel in just a few million years. Others are tiny red dwarfs that will continue shining for trillions of years. The most common type of star in our galaxy is actually the red dwarf, which is smaller and cooler than our Sun. These stars are so dim that none of them are visible to the naked eye from Earth, despite being the most numerous type of star in existence. Planets orbiting red dwarfs would have very different conditions than Earth. To receive enough warmth from their dim parent star, they would need to orbit very close, which could subject them to powerful stellar flares and tidal forces. Hot blue stars, on the other hand, are much rarer but far more luminous. A planet orbiting at a comfortable distance from such a star would need to be much farther out than Earth is from the Sun. These stars also live much shorter lives, typically only a few million years, which may not be enough time for complex life to evolve. The nature of any planets you might find would depend on many factors. Rocky planets like Earth can form close to a star, while gas giants and ice giants typically form farther out where temperatures are lower. But gravitational interactions can cause planets to migrate from their birthplaces, leading to configurations that might seem strange to us. Some star systems have gas giants that orbit closer to their stars than Mercury orbits our Sun, while others have chains of rocky planets packed into tight orbits. One of the most exciting possibilities is finding a planet in the habitable zone of another star, the region where temperatures would allow liquid water to exist on the surface. Astronomers have already identified several potentially habitable planets around nearby stars, though we cannot yet confirm whether any of them actually support life. If we could travel to such a planet and find that it harbored living organisms, it would be the most significant discovery in human history. But let us continue our journey and consider what lies beyond just the nearest stars. Our solar system is located in one of the spiral arms of the Milky Way galaxy, a pinwheel-shaped structure containing hundreds of billions of stars. The Sun orbits the galactic center at a distance of about 26,000 light-years, completing one full orbit every 230 million years. This means that in the entire history of our solar system, it has completed only about 20 trips around the galaxy. If we were to travel toward the center of the galaxy, we would encounter increasingly dense star fields. The core of the Milky Way is a crowded place, with stars packed much more closely together than in our neighborhood. At the very center lies a supermassive black hole called Sagittarius, a star, which contains the mass of about 4 million suns. This black hole is currently quiet, but it can flare up when material falls into it, releasing enormous amounts of energy. Traveling toward the galactic center would be dangerous not only because of the black hole, but also because of the intense radiation from so many nearby stars. The risk of colliding with stellar debris would also increase dramatically in such a crowded environment. The outer regions of the galaxy, by contrast, are much emptier, with stars spaced farther apart and lower levels of radiation. Beyond our own galaxy lie other galaxies, each containing their own billions of stars. The closest major galaxy to ours is the Andromeda galaxy, which is about 2.5 million light-years away. Despite this enormous distance, Andromeda is on a collision course with the Milky Way, and the two galaxies will merge in about 4.5 billion years. This collision will not cause stars to physically impact each other because the spaces between stars are so vast, but it will dramatically reshape both galaxies through gravitational interactions. The scale of intergalactic space is difficult to comprehend. If interstellar space seems empty, intergalactic space is emptier still. The average density of matter between galaxies is only about 1 atom per cubic meter, 10 million times less than in interstellar space. Light from distant galaxies takes millions or billions of years to reach us, meaning that when we look at these objects, we are seeing them as they were in the distant past. The universe itself has a structure that only becomes apparent at the largest scales. Galaxies are not scattered randomly through space, but are organized into clusters and superclusters, which are connected by filaments of matter into a vast cosmic web. Between these structures are enormous voids, regions hundreds of millions of light-years across, that contain almost nothing at all. If we were somehow able to travel across these unimaginable distances, we would eventually encounter the limits of the observable universe. The universe is expanding, and the farther away something is, the faster it appears to be receding from us. At a certain distance, objects are receding faster than the speed of light, not because they are moving through space faster than light, but because space itself is expanding between us and them. Light from these regions will never reach us, no matter how long we wait. This does not mean there is nothing beyond this horizon. The universe almost certainly continues beyond what we can observe, perhaps infinitely. But we can never know what lies beyond the observable universe, because no information from those regions can ever reach us. This is a fundamental limit, not a technological one. Let us return now from these cosmic scales and consider more carefully what leaving the solar system would mean for human experience. The psychological impact of such a journey is something that scientists and science fiction writers have long contemplated. The sense of isolation would be profound. There would be no way to return home within a human lifetime, no way to communicate in real time with loved ones left behind, no possibility of rescue if something went wrong. The time delay for communications would grow longer and longer as you traveled. From the orbit of Neptune, messages take about 4 hours to reach Earth. From the nearest star, they would take over 4 years. Any conversation would be impossible. You could send a message and wait 8 years for a reply. News from home would always be years out of date, and by the time your responses arrived, the situations you were responding to might have changed beyond recognition. The crew of an interstellar mission would need to be remarkably self-sufficient. They would need to be able to maintain all their equipment without resupply, produce all their food and water through closed-loop systems, and provide their own medical care for any condition that might arise. They would need to be able to solve problems that no one on Earth had ever encountered, with no possibility of real-time assistance. The social dynamics of such a mission would be unprecedented. A small group of people would need to live and work together for decades or centuries through all the conflicts and tensions that inevitably arise in any human community. They would need to develop systems of governance and conflict resolution that could remain stable over multiple generations. The children born on such a mission would know Earth only as a distant point of light, a historical memory rather than a living reality. Some researchers have suggested that the psychological challenges of interstellar travel might be mitigated by technologies that do not yet exist. Suspended animation could allow travelers to sleep through the long journey, awakening only when they arrived. Virtual reality could provide simulated environments to relieve the monotony of the voyage. And artificial intelligence could handle many of the routine tasks of operating the spacecraft, reducing the burden on the human crew. But these technologies raise their own questions. If you spent most of your journey in suspended animation, would you still be the same person when you awakened? How would society evolve over centuries of travel if people were awake but disconnected from the culture they left behind? What would it mean to be human in an environment so different from anything our species evolved for? These questions lead us to consider the deeper meaning of leaving the solar system. Why would we want to undertake such a journey? What would be the purpose of sending humans or their descendants into the vast emptiness between the stars? One answer is survival. Our sun will not last forever. In about 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury, Venus, and possibly Earth. Long before this happens, the sun's increasing luminosity will make Earth uninhabitable. If humanity or its descendants wish to survive beyond the death of our sun, we will eventually need to find new homes around other stars. Another answer is curiosity. Humans have always been explorers, driven by an innate desire to see what lies beyond the horizon. From the first migrations out of Africa to the voyages of discovery that connected the continents, our species has constantly pushed into new territories. Interstellar travel would be the ultimate expression of this drive. carrying us across distances that would have been inconceivable to our ancestors. There is also the question of meaning. In a universe so vast and old, human life can seem insignificant. We are tiny creatures on a small planet, orbiting an ordinary star in an unremarkable galaxy. But the very fact that we can contemplate these questions, that we can build instruments to peer into the depths of space and minds to understand what we see, gives us a unique significance. We are the universe becoming aware of itself, and by spreading among the stars, we might ensure that this awareness persists. The challenges of leaving the solar system are immense, but they are not necessarily impossible. Throughout history, humans have accomplished things that once seemed beyond our reach. We have crossed oceans, flown through the air, and walked on the moon. We have split the atom and decoded the genome. The idea of traveling to another star may seem impossible today, but so did many of our current achievements to the generations that came before us. The first steps toward interstellar travel have already been taken. The Voyager spacecraft are now in interstellar space, carrying messages from Earth and demonstrating that objects made by human hands can travel beyond our solar system. Plans are being developed for more ambitious missions, including tiny spacecraft that could be accelerated to significant fractions of the speed of light by powerful lasers. But even as we dream of interstellar voyages, we can learn much about what lies beyond the solar system without physically traveling there. Our telescopes can detect planets orbiting distant stars, analyze the composition of interstellar gas clouds, and map the structure of our galaxy and beyond. Radio telescopes listen for signals that might indicate the presence of intelligent life on other worlds. And computer simulations allow us to explore hypothetical journeys and consider what we might find. The story of what happens when we leave the solar system is still being written. We know that we would pass through regions of space that are stranger and more varied than most people imagine. From the turbulent boundary of the heliosphere to the ancient icy wanderers of the Oort Cloud to the vast emptiness of interstellar space. We know that we would face challenges unlike any our species has encountered, from radiation and isolation to the sheer scale of time and distance involved. But we also know that the universe beyond our solar system is not simply an empty void. It is a place where stars are born and die, where planets form and evolve, where the raw materials of life drift through clouds of gas and dust. It is a place of unimaginable beauty and wonder, waiting to be explored. As you drift toward sleep tonight, consider the position of our small planet in this vast cosmos. We are travelers on a world that is itself traveling through space, orbiting a star that orbits the galaxy, which is itself part of the expanding universe. In a sense, we are already on an interstellar journey, carried along by the motion of our cosmic home. The distances involved in leaving the solar system can seem daunting, even crushing. The nearest star is so far away that its light takes years to reach us. The distances to other galaxies are measured in millions of years of light travel. And the observable universe extends for billions of light years in every direction. Against these scales, a human life seems like the briefest of flickers. But there is another way to think about these distances. Light may take years to reach us from the nearest star, but it does reach us. We can see the light of stars that are millions of light years away. The universe, vast as it is not completely disconnected. Information and influence can flow across even the greatest distances, given enough time. And time is something the universe has in abundance. Our sun has been shining for nearly 5 billion years, and will continue for another 5 billion. The universe itself is nearly 14 billion years old. In this context, even journeys lasting thousands of years are not impossibly long. They are merely very long by human standards. The question of what happens when we leave the solar system is ultimately a question about our place in the universe. Are we trapped on this small planet, or can we spread among the stars? Are we alone in the cosmos, or are there other minds out there contemplating the same questions? What will become of humanity in the millions and billions of years that stretch ahead? These are questions that we cannot fully answer tonight, but they are worth contemplating as you relax into sleep. The universe is vast and ancient and strange, but it is also beautiful and full of wonder. And we, for all our smallness, are part of it. Let us consider now some of the more serene aspects of interstellar space, the qualities that make it not just challenging, but also peaceful and contemplative. The silence of space is perhaps its most striking characteristic. There is no air to carry sound, no wind to whisper or roar. A spacecraft drifting between the stars would experience a silence more profound than anything on Earth, broken only by the mechanical sounds of its own systems. This silence is matched by the stillness. Without the constant changes of weather and seasons that mark life on Earth, time in interstellar space passes differently. There is no dawn or dusk, no summer or winter. The stars shine with the same steady light, unchanging from moment to moment, century to century. This constancy can be seen as monotonous, but it can also be seen as peaceful, a rest from the ceaseless change that characterizes life on a planet. The darkness of interstellar space is not absolute. Although there is no nearby star to light the way, the stars themselves provide illumination. From a spacecraft in deep space, you would be able to see more stars than anyone on Earth has ever seen, thousands upon thousands of points of light filling the sky in every direction. The Milky Way would stretch across the heavens, its ghostly glow revealing the combined light of billions of distant suns. In this darkness, other sources of light become visible that are hidden from Earth by our atmosphere and our sun. The zodiacal light, a faint glow caused by sunlight reflecting off interplanetary dust, would be absent in interstellar space. But the cosmic background radiation, the afterglow of the Big Bang, would permeate the universe, detectable as a faint warmth coming from all directions. This radiation is the oldest light in the universe, emitted nearly 14 billion years ago when the cosmos was young and hot and dense. The cold of interstellar space is also worth contemplating. In the absence of any nearby star, the temperature drops toward absolute zero, the lowest possible temperature where all molecular motion ceases. Space is not quite at absolute zero because the cosmic background radiation keeps it at about 2.7 degrees above this limit. But this is still incredibly cold, cold enough that most gases would freeze solid. Yet, despite this cold, space is not hostile in the way that extreme cold on Earth is hostile. On Earth, cold kills because it draws heat away from your body faster than you can produce it. But in the vacuum of space, there is no matter to conduct heat away from you. An astronaut in space would actually be more at risk from overheating than from freezing, because the heat generated by their body would have no way to escape, except through radiation. The vacuum of interstellar space is itself remarkable. We sometimes think of a vacuum as simply nothing, the absence of matter. But a vacuum is not truly empty. According to quantum mechanics, empty space seethes with virtual particles that pop into existence and disappear again too quickly to be detected directly. This quantum vacuum has measurable effects, including a force called the Casimir effect that pushes two closely spaced metal plates together. The fabric of space-time itself curves and warps in response to the presence of matter and energy. Even in the apparent emptiness of interstellar space, this curvature is present, a legacy of all the matter in the universe, pulling on everything else. A spacecraft drifting through space would follow the curves of space-time, traveling in what feels like a straight line, but is actually a path bent by the gravity of distant stars and galaxies. Gravitational waves also pass through interstellar space, ripples in space-time created by the most violent events in the universe. When two black holes merge or a massive star explodes, they send out waves that travel at the speed of light, stretching and squeezing space as they go. These waves are incredibly faint by the time they reach us, but they have now been detected by sensitive instruments on Earth, opening a new window onto the universe. The environment of interstellar space is shaped by events that happened long ago and far away. The atoms that drift between the stars were created in the hearts of ancient stars that lived and died before our sun was born. The heavier elements, the carbon and oxygen and iron that make up our bodies, were forged in stellar furnaces and scattered into space by supernova explosions. In a very real sense, we are made of stardust, and interstellar space is where that stardust drifts between generations of stars. The interstellar medium also carries a chemical record of the galaxy's history. Astronomers can study the composition of interstellar gas to learn about the processes that created it. They can trace the elements produced by different types of stars, track the distribution of dust grains formed in stellar outflows, and detect molecules that formed in the cold darkness between the stars. This cosmic archaeology reveals a history stretching back billions of years. As you continue to relax, consider the slow processes that shape the interstellar medium. Star-forming regions collapse under their own gravity, drawing in material from the surrounding gas and compressing it until nuclear fusion ignites. The resulting stars shine for millions or billions of years, gradually converting hydrogen into heavier elements. When massive stars die, they expel their processed material back into space, enriching the interstellar medium with new elements that will be incorporated into the next generation of stars and planets. This cycle of stellar birth, life, and death has been ongoing since the first stars formed more than 13 billion years ago. Each generation of stars produces more heavy elements than the last, gradually increasing the metallicity of the interstellar medium. Our sun and its planets formed from material that had been processed through multiple generations of stars, which is why we have access to the heavy elements that make complex chemistry and life possible. The timescales involved in these processes are beyond human comprehension. A star like our sun burns steadily for about 10 billion years. A red dwarf can shine for trillions of years, far longer than the current age of the universe. Even the shortest-lived stars, the hot blue giants, burn for millions of years. In comparison, all of human history, from the first civilizations to the present day, spans only a few thousand years. In interstellar space, time loses much of its meaning. There are no days or years, no seasons or ages. The slow processes of stellar evolution and galactic dynamics unfold over timescales that dwarf any human conception. A journey between the stars might take thousands or millions of years by our reckoning. But to the universe, it would be an instant. This different relationship to time is perhaps the most profound change that would come from leaving the solar system. On Earth, we are accustomed to change and progress, to the rhythm of days and years, to the sense that time is moving forward and carrying us with it. In interstellar space, this sense of time would dissolve. The universe would seem eternal and unchanging, the stars fixed in their places, the darkness complete and permanent. And yet, even in this apparent changelessness, the universe is evolving. Stars are being born in distant nebulae, even as others are dying in supernova explosions. Galaxies are colliding and merging, reshaping themselves over hundreds of millions of years. The universe itself is expanding, carrying galaxies apart from each other at ever-increasing speeds. Change is happening everywhere, just too slowly for us to perceive in our brief lives. Let us now turn to the question of what we might find if we traveled to another star system. Each star is unique, with its own age, composition, and configuration of planets. Some stars are solitary wanderers like our Sun, while others travel in pairs or groups. Some are surrounded by disks of dust and debris, the remnants of planet formation, or the result of collisions between asteroids. Others appear to be alone in space, with no detectable companions of any kind. The planets we might find are equally varied. Some might be rocky worlds like Earth, with solid surfaces and thin atmospheres. Others might be gas giants like Jupiter, with no solid surface at all, just layers of gas growing denser and hotter toward the core. Ice giants like Neptune, water worlds completely covered by global oceans, and volcanic moons heated by tidal forces are all possibilities. The most Earth-like planets would be found in the habitable zones of their stars, the regions where temperatures are right for liquid water to exist. But even within the habitable zone, conditions can vary enormously. A planet might be too dry, with no water at all. It might be too wet, with no land above the global ocean. It might have the wrong atmosphere, too thick or too thin, or composed of the wrong gases. Finding a planet truly similar to Earth would require extraordinary luck. And even if we found such a planet, it might already be occupied. The question of whether life exists elsewhere in the universe is one of the deepest mysteries we face. We know that life arose on Earth relatively quickly after conditions became suitable, which suggests that the origin of life might not be extraordinarily rare. But we have only one example to study, and we cannot be certain whether our experience is typical or exceptional. If life does exist on other planets, it might be very different from life on Earth. The basic chemistry might be similar, based on carbon compounds and liquid water, because these are the most versatile foundation for complex chemistry. But the details could vary enormously. Life on another planet might use different amino acids, different genetic codes, different metabolic pathways. It might be based on silicon instead of carbon, or ammonia instead of water, or some combination we have not imagined. The possibility of intelligent life elsewhere raises even more profound questions. If other intelligent species exist, why have we not detected them? This puzzle, known as the Fermi paradox, has inspired many proposed solutions. Perhaps intelligent life is extremely rare, arising only once or a handful of times in the entire universe. Perhaps intelligent species tend to destroy themselves before they can spread among the stars. Perhaps they exist, but are deliberately hiding from us, or communicating in ways we do not recognize, or simply too far away for any contact to be possible. These questions cannot be answered from our current position within the solar system. To truly understand whether we are alone, we might need to visit other star systems, to examine their planets directly, to search for signs of life in their atmospheres and on their surfaces. This is another motivation for interstellar travel, perhaps the most compelling of all. But even if we never find other life, the journey would be worthwhile. The universe is full of wonders that we can only glimpse from afar. The rings of other planets, the atmospheres of distant worlds, the landscapes of moons and asteroids and comets, the structures of nebulae and star clusters and galaxies. All of these await exploration. Each new discovery reveals something about the nature of the universe and our place within it. As you continue to drift toward sleep, let the vastness of space become a source of comfort rather than anxiety. Yes, the universe is large beyond comprehension, and we are small. But smallness is not the same as insignificance. We are the means by which the universe comes to know itself, the eyes through which it sees, and the minds through which it understands. In contemplating the stars, we fulfill a purpose that transcends our individual lives. The night sky has always been a source of wonder for humanity. Our ancestors looked up at the same stars that we see tonight, though they understood them very differently. They saw patterns in the stars and wove stories about them, myths that helped them make sense of their world and their place within it. We have replaced those myths with scientific understanding, but the wonder remains. Science has not diminished the mystery of the cosmos, but deepened it. We now know that the stars are other suns, some much larger and hotter than our own, others smaller and cooler. We know that many of them are orbited by planets, some of which might be similar to Earth. We know that the universe had a beginning almost 14 billion years ago and has been expanding ever since. We know that it contains forms of matter and energy that we cannot directly see, shaping the structure of galaxies and the fate of the cosmos. Each of these discoveries has opened new questions. We do not know what dark matter and dark energy are, though they make up most of the universe. We do not know how the first stars and galaxies formed from the smooth sea of particles that filled the early universe. We do not know whether there are other universes beyond our own, or whether our universe will expand forever or eventually collapse. These questions may not be answered in our lifetimes, or perhaps ever. The universe may be fundamentally mysterious, with some aspects that lie beyond the reach of human understanding. But this does not diminish the value of seeking answers. The journey of discovery is worthwhile in itself, regardless of whether we ever reach a final destination, and so we return to the question with which we began. What happens if we leave the solar system? We pass through regions of space that are strange and wondrous, from the frothy boundary of the heliosphere to the ancient ice of the Oort Cloud, to the vast emptiness between the stars. We face challenges that would test the limits of human ingenuity and endurance, and we encounter a universe that is larger, older, and more complex than anything we could have imagined. But perhaps the most important thing that happens is a change in perspective. From within the solar system, we see our sun as the center of everything, the source of all light and warmth, the gravitational anchor around which our world revolves. From outside the solar system, we see our sun as just one star among billions, a yellow point of light no different from countless others. This shift in perspective is both humbling and liberating. It is humbling because it reveals how small and insignificant we are in the cosmic scheme of things. Our world, our sun, our entire solar system is a speck of dust in an unimaginably vast universe. All of human history has unfolded on a tiny planet, orbiting an ordinary star, in an unremarkable corner of an average galaxy. But it is also liberating because it frees us from the illusion that we are at the center of everything. The universe does not revolve around us. It does not exist for our benefit. It simply exists, vast and beautiful and indifferent. This realization can be frightening, but it can also be freeing. It allows us to see ourselves as part of something larger, connected to the cosmos in ways that transcend our individual concerns. As you drift into sleep, carry with you this sense of connection. You are made of atoms that were forged in ancient stars, built from carbon and oxygen and iron that were scattered into space by supernova explosions billions of years ago. The water in your body has cycled through countless living things before you and will continue cycling long after you are gone. You are not separate from the universe, but a part of it. A brief eddy in the endless flow of matter and energy. The stars that shine in the night sky are your distant cousins, born from the same primordial gas that gave rise to our sun. The planets that orbit those stars might harbor life that shares a common chemistry with life on Earth. The entire visible universe is connected by light, by gravity, by the quantum fields that underlie all of reality. This connection does not require us to travel between the stars, though someday we might. It exists already, woven into the fabric of space-time itself. We are already part of the interstellar community, even if we have never left our small planet. The light from distant stars falls on our skin. Their gravity subtly influences our world, and the atoms in our bodies testify to our cosmic heritage. Sleep now and dream of stars. Dream of worlds we have never seen, of skies we have never walked beneath. Dream of journeys that span millennia and distances that dwarf anything in our experience. Dream of a universe that is stranger and more wonderful than we can imagine, waiting to be explored. The night is quiet, the stars are bright, and the universe stretches out in all directions, ancient and patient and full of mystery. Somewhere out there, beyond the edge of everything we know, the future awaits. It may be lonely and cold, or it may be full of wonders beyond our imagination. We cannot know until we look, but for now it is enough to rest. The stars will still be there tomorrow, and the day after, and for billions of years to come. The universe has time, and so do we. There is no rush to explore it all tonight. Let the vastness of space be a comfort, a reminder that there is always more to discover, more to understand, more to wonder at. The solar system is our home, our cradle, the place where humanity grew and learned and began to understand its place in the cosmos. But it is not the only home we might have. Beyond its boundaries lies a universe of infinite possibility, waiting for us whenever we are ready. Until then, sleep well, and let the stars watch over you.